In our last lecture we have seen the formal setup of supervised machine learning problems. We have seen what the risk of a classifier is, the true risk. We have looked at what is the base classifier, and we have also defined what consistency means for a classification problem or for a classification algorithm. The next thing we want to look at is called statistical and Bayesian decision theory. And the question we want to ask here is, again, we want to step back a bit from machine learning. We do not yet want to consider what happens if we only have a few data points and we need to reconstruct all this information from few data points. We want to say, assume we had all knowledge of the world, we know all the underlying probability distributions. What would then be the best classifier that we want to find? Like what is it, in which way do we want to design what is the classification rule that we want to have? And the running example that I want to have in this lecture is the following. We assume we have a room full of people. We can, for each person, we can measure the height of this person. So I don't know, I'm 1.68 meters or so. And now this is the only measurement that we can take, the height of a person, and we want to predict whether the person is female or male. So given the height of a person, we want to predict the gender of this person. And again, I would like to ask you to take a minute to think about how you would solve this problem. So someone comes to you and says, given the height of a person, predict whether this person has been male or female. Please think about what would be your solution to this problem. And please switch off the video and try to come up with a solution now. Let's maybe make it a bit more concrete. Assume we know, what we want to assume in this setting is that we know the input distribution, The running example that I want to have in this lecture is we want to predict, given the height of a person, the gender of this person. So we know, like we measure for a person, the person is 1.80 meters. Do you think this person is male or female? This is the machine learning problem that we want to look at. And we want to look at this machine learning problem under the assumption that we know the underlying probability distributions. So for example, we know the class conditional distributions. I have a plot here of the class conditional distributions. So remember, the class conditional distributions is the probability of x given y. So y is the class. We condition on the class. So assume that the class is female. What is the distribution of the x values? In this case, the height of a person for the female population. And I plotted here this is sort of an ideal case. So we assume that the height of people is normally distributed. It looks roughly like this. So we have the female population, which is the red curve, and the male population, which is the blue curve. And we see the two curves are slightly shifted. So on like the mode of the distribution, the highest point of the distribution for females is maybe at 1.60 meters in this case, and the height for the male persons is as 1.80 meters. Now I would like to ask you to think about how you would solve this problem. So assume I tell you the input of a certain, you get to see these probability distributions, and then the question is, if I tell you a certain person is 1.60 meters, would you think this person is male or female? And please think about what your answer would be, and in particular think about why you would come up with your answer. What would be the algorithm behind your reasoning? Please take a switch off the video, take a minute and think about it. I would now like to take you through a number of different approaches, all of which seem more or less plausible but lead to different results. The very first approach, the really naive approach, would be to just look at the prior distribution of the two labels. So it might be that because we're in a lecture of computer science and 90% of the people in this room are male, that you don't even need to look at the recorded height of the person. You would just say, well, everybody here is male. I would simply predict male. And if you make this formal, this means to predict according to the prior probability of your class distributions. So what you do is your rule Fn of x predicts that the label of the person should be male if the probability for being male in your underlying population is larger than the probability of being female in your underlying population. And if it's the other way around, you predict female. So you just check, in my population, do we have more male or more female people, and this is what you predict. You don't even look at the measurement x. This sounds really stupid and typically is not what you would like to have, but think about, there might be situations where this is maybe not the most stupid thing to do, at least if you're looking for the accuracy of your classifier. So in spam detection, like 99% of all the emails that get sent are spam emails. And if you predict for a random email that arrives that it's a spam email, then with 99% probability this is already going to be correct. Now the point is, for spam detection this is not really what we want to have, because we're interested in this other 1% of the emails. But still there might be cases where predicting the majority label is not the worst of all things to do. Visually, this means that if we check the probability, if you simply plot the male and female probability into a bar plot, we select according to the higher bar. And this is maybe the point where I would like to introduce a Matlab demo that I've written and that shows all these different concepts. Let me just see. So this is a demo that we're going to see for the rest of this lecture a number of times. It has many different windows, but for now simply look at the first row. So the first plot here is always the class conditional distribution. This is the one that we have already seen. It is not going to change in the course of this lecture. We always assume, like if we know people are female, then the distribution of the height is this red line, and for male people the distribution is this blue line. What we are going to change in the course of this lecture is the prior distribution. Here in this example, I have an example where we have the same number of male or female people in the room. So the prior distribution of male and female is the same. We cannot really say one population is higher than the other. What you see on the right hand side is then the marginal distribution of x if you omit the conditions on male or female. So this is essentially the sum of red fraction of population times the red density plus blue fraction of population times the blue density. This is what gives you the marginal distribution of x. So if you look at the whole population and just measure what is the height of the persons in your whole population without looking at the gender of the person, then this is the distribution that you would get. Okay? And the naive first thing that we have just said is we classify according to the bars in this particular plot. Whichever bar is larger, this is what we are going to do. In this particular example, if we have the same number of male and female people in the population, we wouldn't even know what to do, but okay, maybe then this would really be a stupid approach. Okay. Now the second approach already makes a bit more sense, and this is what the statisticians would call the maximum likelihood approach. And the idea is simply, we look at these class conditional distributions. This is the first plot that we've seen in the left corner of this Matlab demo. And we simply take the distribution that seems more likely for the given input. So I said we want to know if a person is 1 meter 60, is it going to be a male or a female person? Now if you look at this class conditional distribution, you would say, well, it is much more likely that the person is female than that the person is male. And this is why I want to predict that the person is female if the person is 1 meter 60 high. And this is called the maximum likelihood principle, and formally the rule works as follows. We check whether the probability for the given measurement that we have, 1 meter 60, we check this probability if under the condition that the person is male and under the condition that the person is female, and then we compare. And we take the one for which the gender for which this gives us the higher value. So observe, if you have seen statistics before, this is sort of, it feels like the wrong way around. We say assume we know the person has been female. What is the probability that we get this measurement of 1.60 meters? And the same for male, and then we decide. In many cases, you would like to do it the other way around, because we want to say what is the probability that a person is male given that we have measured the person as 1.60 meters. And this is going to be the next thing. But let's fix this one first. So this is the maximum likelihood principle, and I would like to go back to this Matlab demo here. Okay. Here we see this is essentially, we just look for this plot. We completely ignore all the prior distributions, and we just check visually which of the two curves is higher for this particular input, and this is then what we're going to predict. Now comes the third approach, which is the Bayesian approach, the Bayesian a posteriori criterion. And this does what I just mentioned. It looks at the probability the right way. So essentially what we now want to say is we want to, let's go down to this formula first. We want to know, given that we measure that a person is 1.60 meters, is it more likely that the person is male, or is it more likely that the person is female? And then this is the criterion we use to decide. So given someone is 1.60 meters, is the probability higher that the person is male or that the probability is female? Now, to be able to compute this quantity, we need to first of all compute these posterior probabilities. And I guess all of you know Bayes' formula, and if you don't know it, it's time to look it up again. There is this standard Bayes formula that helps you to turn around the arguments in conditional probability distribution. So the probability that a person is male given the person is 1.60 meters high, you can express it as the probability of being 1.60 meters times under condition that the person is male, times the prior probability that the person is male, divided by the prior probability that the person is 1.60 meters high. This is the standard Bayes formula. You need to know that. If you don't know it, learn it. It is important. I would now again like to show this in the Matlab demo, because now something interesting could happen. So here is what I have plotted here. Here are in the bottom left-hand corner, I plotted the posterior distributions. So the red and blue line is now the posterior distribution. Assume someone is, the probability that a person is female for the red curve, given that she or he has a certain height, and the same for male. So now, if the criterion would be for someone who is 1.60 meters, we check which of these two curves is higher. And this is what we would use to predict. Now in this particular setup, as we have it in this window that is currently open here, it doesn't seem to make a difference. Whether you check whether the class conditional distribution is higher for red or blue, or whether the posterior is higher for red or blue, doesn't really seem to make any difference. And maybe think about for a minute what would we need to change to make a difference here. I'm going to show you the answer. So the answer is going to be these prior probability distributions. If the prior distribution is uniform, we have the same weights for male and female, then the maximum likelihood approach and the Bayesian posterior approach give you the same results. This changes immediately if we change the priors. So let me now bring up a new window where I change the priors. So say like this. So now we have a room full of females and a couple of males. So the prior distribution in our population is 90% of the population consists of females and only 10% of the population consists of males. And now what you can observe is this point where the red and the blue line crosses has been moved to the right. And maybe I just show it again. So this is or maybe how can I do that? I just bring the window even more to here. So this is if we have the same weight, and this is if the weight changes. I just flip a couple of times so you can see it. So please look at the window at the bottom in the bottom row, the first window. This is for the same weight of male and female persons, and this is for the case where we have more females than males. And now let's think about whether this makes sense. So if we have the same number of male and female people in our population, the crossing point here is roughly at 1.70 meters. So it would be at 1.70 meters you would have the same number of males and females, and you would say, well, I don't really know what to predict. If someone is less than 1.70 meters, you would predict female. If it's more than 1.70 meters, you would predict male. This is if we have the same number of people in the room. But now assume the whole room is full of females and there are just 3 males there, and you find someone who's 1.70 meters. Now you would probably say, well, 1.70 meters, if there would be the same number of people, I wouldn't really know whether the person is male or female. But now this whole room is full of females. So it's really much more likely that the person with 1.70 meters is a female person than a male person. And this is why in this figure here in the screen, the crossing point, the intersection point of these 2 lines has been moved to 1.90 meters, I would estimate here. So only when someone is 1.90 meters in this room full of females, you would start to doubt, and you would say, well, if there's a person who's 2 meters, this room is full of females, but I've very rarely seen a female who's 2 meters large, so probably it's still going to be a male. And this point here where these 2 lines intersect, that shows you what is sort of where this decision slips from male to female. And again, maybe just for the fun of it, let's have a population which is the other way around. So we have only, most of the population consists of male persons and only few female persons are in the room. Then this intersection point moves much more to the left-hand side. And you would say, I mean, maybe the crossing point is now with 1.55 meters or so. You would say, well, if a person is 1.40 meters, even though there are only few females in the rooms, it's maybe a female. But for everybody who's larger than 1.55 meters, I would predict male because there are so many males in the room. And this is now the difference between the Bayesian approach and the maximum likelihood approach. The maximum likelihood approach ignores this base rate, this prior probability of the labels that you have in your population. The next thing we would like to take into account is the loss function. We have seen that in machine learning we typically define a loss function that tells us how much we want to punish certain types of errors of our algorithm. And of course, if we know this loss function, and we should design the algorithm such that it can take into account the loss function and maybe can focus on the parts of the space where losses would be particularly costly. So how does this work formally? We define a loss function, L of x, y, y hat. X is the input data, say the height of the person, y is the true label, and y hat is the predicted label. And now we consider the conditional risk. So assume we want to predict the outcome at point x. So we've measured 1.60 meters and we want to construct a classifier for someone who is 1.60 meters. And now we want to compute the risk under the condition that someone is 1.60 meters. So this is the expected loss of the predicted value and the input value y, the true label of the person, if the person is 1.60 meters. So it's a bit tricky here. So capital Y is the random quantity over which we take the expectation. This is the true label of the person. And y hat is the deterministic label that we predict upon seeing the deterministic label lowercase x. And now we consider the expected conditional risk at this point lowercase x. So the risk of this prediction y hat, given that the input is lowercase x, so 1.60 meters, is now is composed of 2 terms, the one of the male population and the one of the female population. So it is under the maybe start with this term here. Given what someone is 1.60 meters, what is the probability that the true label of this person is male times the loss we would make for prediction y hat if the label is male. And then the same for female. So under the condition that someone is 1.60 meters high, what is the probability that this person is female? And then what is this loss that would occur if we predicted y hat and the person would be female? And this expected conditional risk is now what we want to use to predict. So the Bayesian decision rule is to select the label for which this conditional risk is minimal. Let's again look at this in our Matlab implementation. And I go maybe again, first of all, back to the symmetric case, where we have the same prior distributions. So again, here's our window, the conditional distributions as before. The class priors are now equal. The posteriors are also now in the weighted case where we have uniform distributions are the same. And now, hang on, I want to show you this particular plot here. So this is now the bar plot that shows you what the loss is. So we have two cases. Either someone is female but we predict male, or someone is male and we predict female. And I want to give different weights to these particular losses. So here I have written the loss of male if the true label is female. So the color indicates the true label of the person. So if truly a person is female, but we say this person is male, we incur a certain loss, and in this particular case the loss is 1, and the other way around in this particular case as well. Now what we see here in the next plot is the pointwise risk, the blue curve and the red curve for these kind of predictions. And this is the curves that we are going to use if we predict based on the Bayesian decision criterion, on the one that we've just been discussing, where we look at the conditional risk. And to see what is going to happen, I would again like to change some things. So now let's look at the case where the losses are not really the same. So here now, if someone is female but we predict male, we don't really incur a big loss. But if someone is male, the true label is male, but we predict female, we incur a really big loss. And now I'm going to flip between this situation and the symmetric situation where the loss was the same in both cases. And please observe this kind of plot, the third plot in the bottom row. I'm simply going to flip between a number of situations. So this is the case where we have the same loss, and this is the case with a different loss. And again, look at how the plots flip. You can see that this blue curve is going to change, and that this intersection point here moves more towards the left. And now this makes sense. So the question is, so what we plot here is the risk. And now if the majority of the if the loss, if it's much worse, if you predict that someone, so the loss is very bad if someone is male but we predict female. So the likelihood that when we predict female that we make a loss is in principle higher than if we predict male. So the risk here increases when we predict females, and it increases more than for the males. Whereas if we have the other way around, let's see, maybe I do it the other extreme case. Now we have the case where if someone is female and we predict male, we do not make any loss. If someone is female and we predict male, we incur a big loss. If someone is male and we predict female, we do not incur such a big loss. And now if you look at the pointwise risk, predicting that someone is male has a much higher risk, because here we incur a big cost, whereas if we predict male we do not incur such a big cost. So this is now if we have the same population in the same male and female population. Now this also is going to interact with the population, and this is now when it gets really complicated. So let's maybe look at this. So now I change also the prior distribution here of the two populations. So what we have now is we have a much higher population that is female and few people that are male. And for the females, if we predict that they are males, we incur really a big loss. So essentially this means that the risk for predicting male is much larger than the risk for predicting female. And only when someone is, I don't know, 2.20 m or whatever this is here, we would dare to say that someone is male. And for everybody else who's below 2.20 m, we would say female, because we have so many females in the room. And if we get the females wrong, the error is so high that we simply cannot afford this. Now let's maybe play the other way around. If we have the population is the other way around. Now we have few females in the room, many males in the room, but still getting the females wrong is bad. But now, as opposed to the case we had earlier, because there are not so many females in the room, maybe it's not too bad if after all we predict male from time to time. So here now the intersection point where we predict male has moved to the left again. So again, remember here we predict according to what is the lower of the curves, where the risk is smaller. And now from 1 meter 75 or whatever on, we would predict that someone is male, and before that we would predict female. Okay. There's one more plot that I haven't really explained yet. This is the plot here at the very right hand side. This is the overall risk at a given threshold. So what we show in this plot is, assume we put the decision threshold at 1 meter 70, say. Then the overall loss that we would occur with these kind of parameters would be 0.45, a bit below 0.5. If we would put the classification threshold at 1 meter 50, we would incur a much higher loss, namely 1.5 on average. So this is sort of, given a particular decision threshold, what is going to be the loss. And again, here you can see how this curve changes. I maybe go back to the other extreme scenario, to this one here. This was where the population is unbalanced towards females, and the loss is also much worse for females, if we get females wrong. And then the risk decreases for a very, very long time until we're at 2 meter 20 or so, and it always gets, like, essentially this means if you put the decision threshold at about 2 meter 20, then this is the smallest loss according to at least for the parameters that we have in this plot. And maybe again, let's make everything symmetric again, so we can see again how a more normal situation would behave. So now I made again the female and male population have the same size, and I made the loss symmetric in both cases. And now you see that depending on your threshold, you can have different risks, and the smallest risk is when your threshold is around 1 meter 70 or so. Then you incur a loss of 0.15 maybe, and the loss increases, or the risk increases if you go to the more extreme sides.